Welcome to the Cycle World podcast. I'm Mark Hoyer. I'm with our technical editor, Kevin Cameron. We're doing part 2 of a podcast this week. A number of weeks ago, we did essentially what was old made new. Technology you think is new, but is actually perhaps a century old or more. We have the second part of that list. Kindly, one of our fans said, I made a joke that we could do a 13-hour podcast on these if we did the whole list. And he said, well, get with it.
Yes.
Would probably help the RPM or revenue per thousand if we did it that long. But we know you got other things to do. So we broke it up into 2. And we'll get going after we say thank you to Octane Lending for sponsoring this podcast. There's a link in our description. You can shop for a motorcycle and see what you could pre-qualify for to finance a motorcycle. So check it out. Click the link. We're going to start with something that is near and dear to me, but also far, far away. So most of the motorcycles I own have flat tappets. And there's much ado in the current market because oil has evolved. They've everything has roller tappets, and they've tried to take all the, let's say, catalyzer poisoning things out of oil. And it's all like pond water now. It's all 0W20. Yep. And I just rebuilt the Ford 460 in my F-250 and put it back in. And we took many measures to make sure that the flat tappets would not flatten a cam, because there is an epidemic of cam flattening, and you have to you get your zinc heavy oil and you put your zinc ZDDP stuff in, and then you go right to 2000 and you hold it for 20 minutes, half an hour, shut her down, make sure everything's good, and then you drive it and you keep it spinning. We can avoid all that with roller tappets, and you'd think we did roller tappets last week or 5 years ago, but no. Is it 1894?
Yes. Yes, it was 1894.
Holy moly.
Stephen Balzer was a Hungarian immigrant who trained as a watchmaker at Tiffany's. Remember the movie Breakfast at Tiffany's? And with Audrey Hepburn. Well, in 1894, Balzer built a 3-cylinder rotary powered car, the first automobile to operate in New York City. And he was later contracted by Professor Langley to produce a more powerful engine for his aerodrome, which was going to be launched off of a houseboat floating on the Potomac. And they made several efforts. They developed a marvelous engine that made excellent power per weight, but it came to nothing because it didn't fly. It hooked on stuff as it went down the launching track and tore the tail off. So I think the pre-flight was missing something.
There's a lot, you got to take care of a lot of details with an aircraft.
Yeah. Fuel boost pumps on.
Yeah. Well, that's why we have massive checklists, because the consequences are real.
Indeed they are. And then in 1908, the Séguin brothers, it looks like Seguin, Laurent and Louis, produced the 50 Gnome, which was a rotary engine that was the precursor for all of the rotary engines that powered so many World War I fighters. If you've ever seen those flying circus movies with the daring young men and no parachutes, it was believed that people would jump out of their airplane rather than try to save it. Expensive things, these airplanes. Anyway, it had roller finger tappets, roller levers, and they looked just like the roller lever tappets used in the first version of Harley's 8-valve board track racer. And the last version used what they called at the time direct action tappets, which were parallel to and coaxial with the push rods, and they had rollers on the end. And the great thing about rollers, as you were just pointing out, is that they don't have to be generously lubricated. They can sort of squeak along until the next splash of oil comes flying off the crankshaft. And so thousands and thousands of those rotary engines were built for that war. And today we have just said farewell to the Harley Sportster, which had 4 separate cams all geared together, each cam with one lobe on it, lifting one hydraulic tappet, and to give the Sportster those 2 pairs of parallel pushrod tubes that were a Sportster feature.
Well, and not a bad idea on a pushrod engine, so that they don't get a wave by being crossed over, right?
Yeah.
If they're at an angle, they would tend to wave, and especially if they're long, if you really rev them up. I mean,
and this is why pushrods are frequently made barrel shaped, noticeably fatter in the center than at the ends, in order to stiffen them up against lateral resonance bending. You get a pushrod whipping back and forth, you've lost valve control. So the roller tappet has made something of a comeback because a lot of cars are operating on the freeway at RPM that would produce significantly more drag on a flat tappet cam than if it were a roller cam.
Let's talk about that. So I have this cap to a spray can here, and we'll say this is a flat tappet. And then what you're doing is having the camshaft. So I'm just, for you Spotifyers, I'm just holding a cap to a spray can, and my fist is the camshaft. And you're turning, and the tappet is in a bore, and it's sliding up over the peak, and then it goes back down, and it goes around the heel where there's usually clearance. And a lot of times there's an oil hole on the heel that's putting oil out and allowing the flat tappet to ride on a film of oil until the next time the thing spins around. I have seen race engines with auxiliary oiling in a billet block, long way drilled, and then it has sprayers at every cam, and they pressurize that, and it's just hosing the cam with oil all the time. A roller tappet puts a roller in between this part of the tappet and the cam, and it rolls around just as it says, and it has the advantages that Kevin has talked about.
It's possible also to make hollow flank cams, and hollow flank cams don't work with flat tappets because they'll be bridging the valley during one part of the lift curve. So anything that has a concavity in the cam form, such as the cam rings in radial aircraft engines, a ring with a series of ba-dum, 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 lift curves all the way around it. And then the problem today, folks, for this surprise hour exam is to figure out the gear ratio and the number of lobes required for an 18-cylinder engine.
Oh, that'd be fun, yeah. Well, I have one of those rings inside the transmission of my 1966 Jaguar Mark II with overdrive. And it has an oil pump that runs on a giant ring like that, and a little roller at the top. And as you spin it around, it makes the oil pressure that operates the cone clutches to engage and disengage the planetary gear that gives you the overdrive, 28% in this case, which is a very nice number, I gotta say. When you hit that electric solenoid and it engages the oil pressure to the cones, it goes, wah, and off you go, 85 miles an hour.
Wonderful.
Flat tappet engine, overhead cam, bucket shim.
Yep.
Do you know Aston Martin's, the Aston Martin inline 6 of the DB5, DB4, James Bond and all that? Very, very old school. So in a Jaguar, you take the shim, you take the bucket off, and you put a shim underneath that fits in this nice little pocket, and you can adjust your valve clearances that way, which is very common on a lot of Japanese motorcycles, the double overhead cam stuff that we have enjoyed for so long.
Yep.
At Aston Martin's, you machine the tappet. You do your math, and if it's too short, you get another tappet.
Yes.
And you start over. Handmade, beautiful,
Till you get
English.
it right.
Yeah.
Until the next tappet set or next clearance setting interval comes up.
Yeah.
When you have to do it again. And of course, that was the motivation for Ducati to come up with a longer service interval, because people were moaning about having to clearance those Desmo systems. And
Well, I don't remember the inner. I'm sorry. Go ahead.
I attended a day of service school, and they had the special pliers that enable you to load the retainer against the split collets and the valve stem, so they are all fully seated, so you don't get a false piece of information. You're measuring with the shim stock. Oh, that's good. Then you start the engine. Suddenly the clearance is hugely greater because those things weren't seated. So this special purpose thing had made a satisfying crunch.
It's a neat system.
Yep.
My 900 SS, I believe, is 10,000 kilometers or 6,200 miles for checking the valve clearances.
Yep.
I did it as soon as I got the bike, because I got it with 853 miles, and I thought, well, let's just make sure we know what we're dealing with. I got it with 853 miles 2 years ago, in 1995. I went to the press launch of the Super Sport 1000, the Pierre Terblanche design of the next generation Super Sport circa 98, 99. And it was at Laguna Seca, and we had our presentation. Andrea Forni, the test rider, was there, and he said, we have updated the seats of this engine. In addition, there was lots about that engine that was improved. The castings were nicer. There were a lot of changes. But they went to a beryllium bronze valve seat, and it extended the interval, the checking interval.
Yeah.
Beryllium is, don't eat it. It's very toxic, but it's also got a lot of qualities that we would like inside of our engines.
An extremely high Young's modulus, which is why they made electronic racks for satellites out of that stuff. Wonderful. Anyway.
Well, we could talk about Young's modulus, but
yes, we'll leave that for another day. But roller tappets continue to have a place, as I mentioned. In case of automobiles rolling along the freeway, it reduces somewhat cam drive friction. But of course, it's like anything that is planing on a liquid. It's speed dependent. The reason why people originally had to go ding, ding with the throttle all the time was to keep everything lubricated. When you winged it, there'd be a lot of friction, but when you rolled off, as you made this cyclic performance, oil would enter the area, and the thing would be lubricated. But if it just sat there idling, dum, it would tighten up.
Yeah. So, well, back in the day, we did this because we had terrible lubrication. Yeah. We didn't have. So I'm going to kick us into the next topic, and I'm going to skip the one that's next on the list and go right to pumped recirculating oil systems. Frederick Lanchester, the man who invented everything, is what Kevin called him.
A lot of inventions you look at that are automotive in nature, and some that are aerodynamic. There's old Fred popping his head up again, because he never had an idea, apparently, without writing it down at once. And one of the ideas was pumped recirculating oil systems. Originally, you may have seen farm engines that had a grease cup on the connecting rod big end. Stop the engine and give the grease cup a turn and a half. Grease enters the bearing. You're good for the next hour.
Oh, grease cup on the distributor for the Aston Martin, grease cup on the distributor for my Austin Healey, quarter turn every whatever, packet full of fresh, and you just turned it till once it bottomed, unscrew the cap, Pack it with grease, get
Yes.
it in there, wipe it all off. Yeah, grease caps. Love it. Oh,
And of course, those were the days when your car needed service every 11,000 miles or 1,200 miles. And people just accepted that. Oil change, yes. Set the point, set the dwell, set the gap. Oh, dear. Um, and now we've gotten used to practically zero service, and the temptation is to let your car run out of oil. So,
well, who opens the hood? I mean,
yeah,
I don't know. I mean, we've
yeah.
got a modern,
How do you do that?
I got a modern Japanese 4x4, and it's like I can't help it. I open the hood and I check the oil, and you know, we've run synthetic. I'm like, oh, I'll see what it looks like after 8,000 miles, because the actual interval is 10,000 miles, but I feel
Yeah,
like, well, I shouldn't do that. And so I look at it at 8,000 miles. I look at it at 5, and it looks like I just put it in. It's
yeah,
so clean. The oil, the combustion control, the ring sealing and the chamber sealing is so good that you don't, and it never deviates. Like at 10,000 miles, it hasn't used any oil. I mean, nothing.
yeah.
It's exactly where I said it. And I'm like, huh,
We're spoiled.
yeah. Anybody need a drink? Try that with your Veloset.
Well, in the early days of motorcycles, you put a couple of ounces of oil into the crankcase, and if you could start the engine, you rode off. And as you rode along, the oil would be whirled about by the crankshaft, and various little troughs and holes were arranged so that flung oil would enter the timing case to lubricate the cams and tappets and the gears that drove the cam. So it was an okay system. And as its proponents argued, it said only clean, fresh oil touches your engine.
What I love about some of those systems is there was a little fitting with a glass dome that you could see that came up next to the tank or through the tank,
Yep.
and you could see the oil coming out of a spout and hitting the glass, and that
Yes.
you knew that there was still oil by this happening.
Yes.
And if it
Whereas
stopped, you're
in the olden times, the way you could tell if you needed to give a shot of oil with the hand pump, later it was a foot pump because you might want your hands for some other duty, uh, you're advised to look back. If it's not smoking, give it a shot of oil. Because these engines did not have oil scraper rings. So, and that's why engines had to be decarbonized in those days at regular intervals because they threw so much carbon. The exhaust ports and so forth would be caked with hard carbon. It would be in the combustion chamber. You have to open it up, find your little paint scraper, and
so you
get
say
it
like
off.
in the olden days. So he said oil scraper, that's on the piston
Yeah.
separating the oiling area from the combustion chamber. We
Yes, sir.
have, compression, and in those days it might have been compression, oil control, compression, or no oil control, as he
Yep.
pointed out.
Yep.
And
A lot of
then
rings.
and you need to decoke. And he talks about like this is like ancient times. The Triumph TR7 in the late 70s and early 80s had an incredibly short, I forget what it is, but it's like remove the cylinder head and decoke it at like 10,000 miles.
Yeah.
No wonder they're out of business.
They wanted
In
you
night,
to participate in the life of your motorcycle.
well, I'm all for it. I am.
Yes, well, we know that.
If there's a complicated way to get something simple done, I'm in.
They didn't modernize motorcycle oil systems, so we're told, because they thought it would make them too expensive and people would say, forget it, I'm not going to join the motoring generation. But eventually it was such a shock that recirculating oil systems were accepted for motorcycles, and Harley Davidson gave their 61E of 1936 such a system. And the following year, having 1 year's experience with it, they decided to convert all their models to recirculating oil. So once it was properly looked at by the industry, they decided, well, this is a great advantage. Let's have it. Why haven't we been doing this for years?
Well, thank goodness, because look at us now.
And of course, in those days, there were no filters, there were no oil coolers. It was just moving the oil around, making sure that oil was getting to the big end bearing through drillings in the crankshaft or through pickup rings on the flywheels. A variety of supposedly money-saving partial solutions were adhered to.
I'm going to go ahead and say it, Kevin. When you have roller bearings and all that, you don't have to worry about asperities as much.
Yeah. Yes.
Ding.
As long as sand isn't entering the engine somewhere.
Well, yeah, they were. I mean, back in the day, open rockers. I mean, everything was kind of exposed. You had tappets that were just sitting there doing their thing. You could just look at them going, flipping around.
And yet, when Rudolf Schleicher built his OHV BMW, it had rocker covers. It was a modern engine in terms of lubrication. It had a pumped recirculating system, and you didn't have to lubricate the rocker arms with a little boink, boink, a little oil can. And why didn't that catch on?
Well, it's a rider aid, though. Like you.
Yes, that's right.
I need to oil my rockers while I'm riding, or else I'm not actually in control of the motorcycle.
That's it.
We did a Rider Aid podcast. You should go listen to it. I'm being a little glib here, but it's true.
Yeah.
All right. Spline shafts. We're moving on to our next topic. Spline shafts. Now, splines are great. And if you've ever worked on a British motorcycle and you set the gear on the magneto, there's no key. It's just a tapered shaft. And you're supposed to tap it with a hammer to set the taper and then scooch it down. And that's supposed to keep you in time until the next time you got to check it.
And sometimes they would say, it may vary a little bit during the first 50 or 100 miles, but she'll come right soon. Wishing will make it so.
Tell us about spline shafts.
Well, for a variety of purposes, it was desirable to have something on a shaft that was unable to rotate but could slide axially. And a good blacksmith could forge a square shaft and make a wheel or a potential gear with a square hole in it. Another possibility would be a keyway. We know that all those early motorcycle engines, the main shafts, the flywheels, and the crankpin were joined together by tapers and keys. And the whole thing was nutted to make sure that it didn't just completely fall apart. Well, I have seen older machine tools in which there's a long shaft which has had a slot milled in it and a piece of 1/4 by 1/4 key stock tapped lightly into that slot, and that locks the shaft to a gear or a pulley or something else that is free to slide along the shaft. Lathes needed to have change gears by which you could cut screws of different thread pitches depending upon how fast the lead screw was driven by the gearbox. And so splines were a useful thing there because you could engage certain gears and disengage others. So on the other hand, splines are expensive. When Yamaha were building their vertically split twins, the YDS series, they had splines on the crankshaft driving the primary drive. And when 1970 rolled around and they did R5, they did away with that. And instead they had a great big whacking key in a key slot. And there was never any trouble with it, to my knowledge. I've looked at a lot of those crankshafts, and I've never seen one of those things that failed. So all of those splines that were cut with I won't call it loving care, with machine love, were unnecessary expense.
Well,
And
I think the only thing more expensive than cutting the spline is broaching the other part.
yes,
right? I mean,
well, the brooch is a pretty specialized piece of work. A lot of them are.
so that's the female that fits the spline. Like you have a spline, you got to have a part that fits on it. So you
Yes.
cut the spline, but then you need a broach that will, you machine a hole and the broach would go in and cut
You pull the
teeth.
brooch through with tremendous force. And each row of teeth would have slightly taller dimensions than the one before it. So each one would remove a chip as it until the splines were cut to full depth. Done. Well, in a primitive motorcycle gearbox, some of the Indian gearboxes actually crashed the gear teeth into and out of engagement. That is no longer done. That's a terrible no-no because, of course, the ends of the teeth are quickly rounded off or broken or chipped. So this is where we get the description constant mesh. A common 6-speed manual shift gearbox for a motorcycle has 2 parallel shafts. They're both splined. Each shaft has a combination of gears that are free spinning on the shaft but are confined by circlips so they can't slide along it, and gears whose position along the shaft is determined by a shift fork which rides in a groove cut in one part of the gear. It's a clearance fit, so when it's lubricated, it lasts forever, provided you're not one of these people that uses the heel of his boot to engage first, and then second, third, and so forth. And the shift drum, it used to be a shift plate, but basically it's a rotating device with cam slots that move the shift forks in such a way that you can select first, neutral, second, third, fourth, etc. And it is sequential. You can't shift from second to fifth, for example, whereas with an automotive style shift pattern, you can shift from any gear to any other. And splines are necessary for this type of gearbox. But here's the thing that's interesting, and that is that Indian's first gearbox, which was a 2-speed, was used on the bikes that finished 1, 2, 3 in the Isle of Man TT in 1911. And splines, sliding engagement members, it was all tremendously advanced. And that is a separate subject, which we'll talk about in a minute, called dog ring shifting. But it has to do with movable elements that are splined to the shaft, and when they're put into engagement with the engaging dogs of the next door gear, the neighbor gear, will lock it to the shaft also. So you can, by a combination of these movements, select all the 6 gears plus neutral. So the problem with splines and keys is that if there's shock and a lot of torque involved, the bottom of these slots or key slots have sharp right angle shapes. You've got a Woodruff key cutter, which is a special purpose rotating cutter with several edges, and you've got the tapered shaft that you're going to mount your ignition rotor on, and you lower this thing down into the metal and it cuts the key slot to the desired depth. You're done. But I've seen a lot of those shafts that have broken at the key slot, and the crack has formed at the sharp edge where the wall and the bottom of the key slot meet. So this has led to the development of involute splines.
I was just going to say involute. What do you know? I thought I was going to be able to bust that out and impress you, Kevin, but
well, I'm
nope.
impressed. I'm impressed. Involute gear profiles are very old, and they were sort of discovered when Dutch mill operators found that wooden gears naturally wore to a contour of sort of minimum energy. And they put some numbers guys on this, and they came up with some ideas. But the nice thing about an involute gear or spline is that the contour of the gear's flank goes down to the bottom of the tooth space, and it is smoothly rounded. There's no sharp edge there. So this means a tremendous increase in the ability to withstand fatigue. Now we know that in a crankshaft, for example, the crank pin is cylindrical, and yet it is part of the crank cheeks that are on either side of it. Does it flare out into the crank cheeks, or is there to be a right angle there so we can make the bearing the full width of that space? Well, people tried to make the bearing the full width. The cranks developed cracks at that sharp edge, at that right angle, and if run long enough, they broke in half. And they said, okay, we've got to have a smoothly rounded shape there, just like at the bottom of gear teeth. So involute splines have another advantage, and this was recited to me by Steve Scheibe, who worked so hard to make the VR 1000 Harley Superbike successful. He said involute splines can be rolled. They don't have to be machined.
Oh, even better.
And of course, very fine splines are found in jet engine shafts to couple various parts of how do you drive the fan? You know, do you put a flange on the shaft and bolt it? Do you spline the inside? Who knows? Anyway, very fine splines and high fatigue resistance because they don't have those sharp corners at the bottom of the splines. Of course, then when you look at a motorcycle gearbox, you think, well, wait a minute. Yeah, we get rid of those sharp edges, but now we have to have circlip grooves. They have sharp bottoms. You can't win.
Well, we can just contour and roll everything and put a radius on all of it, and it'll just take extra time to make it fit.
Well, people do it when they have to.
Yeah.
And they've learned through discouraging failures that they have to.
Well, it's like with castings. I mean, when we couldn't do controlled fill and all that, we have a like a Magic of Metals. We've done a casting podcast you can go back and listen to. But castings, you know, when we were just pouring them in a big mold and air is everywhere, and you're getting entrained oxides, which means trapping oxides inside the casting, and they would crack. You just made them thicker, and that's why castings weighed so much. But now we have all this magic pressure, vacuum, suction, and it's amazing. So it's
no more entrained oxides. That's
yeah,
the
you
thing.
just make them bit. But when you're not working with that, you
just make it thicker. Yeah,
just make it thicker.
It stops breaking.
You make the shaft bigger, and then you just try to cope. You just got to use more material. All right, we're going to get to our next one. And this is interesting. This kind of probably led to all the cooling that we ever wanted, but, you know, with liquid cooling, etc. But engine oil cooler, patented by Benelli in 1931 for motorcycle use.
Yeah.
Amazing.
Well, what you find if you use an engine hard, its temperature rises. If it's an air-cooled engine and it's summer, it rises even more. The higher the temperature rises, the lower the viscosity of the oil falls until possibly you reach a point at which it can no longer provide a full film of lubrication between the moving parts where it's needed. So what are you going to do? Well, we'll put Harley oil in there, 50 weight. That's a solution. Another solution is to cool the oil so that it remains at a temperature at which it lubricates well. That's a solution. And it was adopted by Benelli because on their race engines, they'd had the lubrication problems. It was adopted in aviation, where it was discovered eventually that they were 30% of the heat, waste heat generated by the engine, was going out through the oil cooler. And because it gets really cold at higher altitudes, they had to have a door on the oil cooler so that they could vary the effect. And it's been known that the controls to those doors could fail. This is why we say, with respect to machinery, just do everything perfectly, then you're in with a chance. So the oil cooler is a wonderful thing because, as the people at Velocet discovered when they first circulated oil throughout the engine, it makes the parts of the engine that are too cool, for example, not warm enough to evaporate gasoline, makes those parts warmer, and it makes the parts that are too hot, such as the exhaust valve seat and the metal around the exhaust port, it makes them cooler. So it has a leveling effect on temperature. And this was the basis for the oil-cooled Suzuki GSXRs, the very first ones from '86, were oil-cooled because the engineer in charge of that aspect of the engine knew all about World War II big air-cooled radials and how much heat they were able to take out of it, how much cooling effect they could get from an oil cooler, because the oil was everywhere in the engine.
I think the most beautiful fin pitch on the early GSXRs, very fine.
Yeah.
Finest I've seen on a motorcycle, personally.
Well, they're not deep, so it's not as bad to have the fine pitch, I suspect. But
because we're normally at what, a quarter inch or something.
Yes, they are. Yeah.
Quarter-inch pitch, this means the space in between the fins. So if you make it really fine, if they're shorter, then the air can get in there and circulate around. But if you have a deep fin, take your RD 350 or your Harley or whatever, getting a quarter-inch, it lets the air actually get in there. So that's a bonus.
Yes, because otherwise it's just for looks and doesn't work. So the thing about oil cooling, of course, is you want to control oil viscosity to make sure that you have good lubrication. And an oil cooler is a tool that can be used for that. Another tool, it's an oil cooler by any other name, is a deep finned sump. When I was allowed to examine the RC 165 Honda 6 that was at the a museum in Canada, I could see that it had extra fin area welded to the oil sump. They were having a lot of trouble with engine cooling in those days. And eventually in '67, when I went to the Canadian Grand Prix at Mosport, the hot running engines were equipped with oil coolers in either side of the lower fairing. So when they'd pull the lower fairing loose, somebody would reach in and pull the oil coolers out of their slots in the fiberglass fairing, and then the fairing would be taken away, and the oil coolers would dangle by their hose connections. And I was so delighted to see this because I was a classic ignorant youth thirsting for knowledge, and here it was. I could see these wonderful machines. That's why I went to that race, to see the Grand Prix bikes. And MV Augusta, as they narrowed their valve angle after 1970, they were no longer able to get cooling air down into fins between the two cam boxes. And so suddenly they sprouted oil coolers in the nose of the fairing. They drilled 100 holes in the number plate to let this little whistling fingers of air come in there and cool this. But they basically had to cool the head with circulated engine oil.
Well, it's
whereas
also lighter.
Whereas before they had cooled it with all these fins. Yes, pick up a fin cylinder. Those things are not light. So the basic goal, of course, of cooling is to keep things from getting hotter until they fail. And first among them is the oil, the key to everything. When for another video some years ago, we took apart a CBR 600RR Honda engine that had 26,000 miles on it. We marveled at how oil was circulated everywhere in that engine and at the wonderful condition of the parts. Cams, tappets, pistons, cylinder bores, crankshaft all looked lovely. All you have to do is make sure that there's good quality oil present everywhere at a reasonable temperature. What's not to like? That oil film between the parts prevents them from wearing. When does the wear take place? When you start the engine. My paternal grandfather was given a state car by Indiana. He was a state engineer, and he'd had it up to here with cars that wouldn't stay running after they started. So, he would floor it. And his cars only lasted a few months because he just ripped the daylights out of them with his starting technique. Sad but true. Oh, we're coming to a big one.
Go ahead.
How many valves per cylinder?
I guess as many as you like.
Yes, the optimum solution is what's left after you've experienced all imaginable failures. But when any technology is new and fresh, you see a great variety of approaches to implementing it. And so during the period between 1895 and the beginning of World War I in 1914, the French were the foremost, but by no means the only, experimenters, making engines with as many as 8 valves per cylinder. Sometimes there would be 2 side valves in pairs on either side of the cylinder, plus valves in the head. They had valves delage, like to put their valves in like this so that their stems had a 180-degree included angle. Because the combustion chambers in a low compression engine, 5 or 6 to 1, there was room to stick the valves in sideways. And they tried all this stuff for 1913. 3 French racing drivers and a design draftsman joined together and chose from among these features the ones they felt would be cooperative in producing a good engine. Peugeot built this engine for them. It had double overhead cams. It had 4 valves per cylinder. 6 valves, 5 valves, too many. 4 valves, just right. Because they were small enough to cool decently. Great big valves gather a lot of heat from their surface area. Small enough to cool decently, small enough to follow the cam with a reasonable spring. And they flowed a fair amount of air, even with the poor port design of that period. So they won the French Grand Prix in 13, or was it 12? I don't recall. But by 1914, hardly any of the engines on the starting line for the French Grand Prix deviated from this new norm. 4 valves, double overhead camshaft. And when one of the racing Peugeots happened to be wrecked in America, and they looked around for someone who thought he could repair it, old man Miller put up his hand.
Harry Miller.
Harry Miller, who always was so dapper with a little mustache that looked like he was some kind of functionary in Hollywood. And he did wonderful work. The car raced again. And that was the origin of what we came to know as the Offenhauser 4, which had the tunnel crankcase that the Peugeot had. You put the crankshaft in from one end. It had 4 cylinders. It had 4 valves per cylinder and double overhead cams. And those things were running all the way into the 70s, I think, in turbo form. I remember that the man we called the Champion Man was very experienced in Offenhauser stuff because he was the spark plug guy when they were developing the turbo Offie. So that influence from that 1912, 1913 car that resulted from those practical people, the drivers, and the design draftsmen, considering the vast number of alternatives, they came up with something that was very workable. And so when World War I was fought in the air, many of the German engines were water-cooled 6s with 4 valves per cylinder and overhead camshaft. It was the norm. But somebody always comes along to mess with it. And in this case, people at Fiat were getting ready to go Grand Prix racing in the early 20s. And lo and behold, they found they could get more air through a single intake located in a hemispherical combustion chamber. I'm not sure they knew why, but we do now that the flow coming out from under the valve, instead of forming a free jet, which is pinched from all sides by atmospheric pressure, it attached to the inside of the head, which functioned as half a diffuser to allow velocity in the intake stream to become pressure. It made an efficient flow situation. And the Fiat 405 or 6 engine was very successful, and suddenly everyone was doing it. And among them were the originators of what would become the Gilera 4. It was given 2 valves per cylinder and a 96-degree valve included angle. Big one. I was so thrilled in those days to see a Jaguar cylinder head with the 2 cam boxes jutting out that said, "I am racy."
They're beautiful.
They are beautiful, even if they're wrong. But they weren't wrong then. They're only wrong now. So this suddenly 4 valves were out, 2 valves were in, and everyone was doing it. Until Honda had a special problem. They built a 4-cylinder racing engine to win the Japan's great volcano race, which was the Suzuki 8 Hours of that period, the 1950s. And it took place on a cinder surface where the rear tire was constantly bouncing, and so was the tack needle. In this period, 2-valve MVs frequently had only 300 RPM between peak power and valve bounce. That is, bouncing against the piston crowns. So this was a problem, a mechanical problem. They needed an engine that could tolerate this over-revving without wrecking itself. And one of the things they tried was 4 valves per cylinder. Hot damn, it worked. They could make it able to tolerate a 2,000 or 3,000 RPM over rev and keep right on going. So the Europeans, meanwhile, were looking down their noses at this deviation from the known truth and saying, well, clearly the news about airflow hasn't reached these distant lands. But in fact, the people in the distant lands knew that they could combine as much airflow as they needed just by making the valves bigger. They could make the bore a little bit bigger, and Honda kept doing it.
Yeah. Surprise.
Yes.
Here we come.
Until at the end of Honda's period in Grand Prix racing with their air-cooled engines, what had been a 1-to-1 bore-stroke ratio became 1.4. And this is why I so much wish that I had had some conversation with Shoichiro Iramadri, because he was one of the people that pushed this trend. Bigger bores, to make room for valves big enough to flow the necessary air, and using 4 valves because it gives better mechanical control of valve motion. Even in the sneered at pent roof head. So 1961 Formula One cars went to 1500 cc's. So how are you going to make, if there ain't no replacement for displacement, what do? You rev the daylights out of it. That's what you do. You perform the power producing cycle more times per second. And so they're looking at Honda and they're saying to themselves, maybe these people from distant lands are a lot smarter than we thought. Why don't we build one of these 4-valve things? We won't tell anyone about it in case it fails. That way we won't look like idiots. So they tested it. They made it work. And soon, everyone was building 4-valve Formula One engines. And then along comes Keith Duckworth, a man filled with self-confidence, but seeking knowledge in a genuine way. He tried for 2 years to make his engine, 2-valve engine, burn well, burn quickly by using squish alone. Then he came up with his 4-valve, narrow valve angle, flat combustion chamber. It burned fast because if he got the downdraft angle of the intake ports right and got the velocity in those ports right, that high velocity would go into the cylinder, strike the far cylinder wall, go down to the piston, and form a tumble motion. They called it barrel motion at the time, and they didn't tell anyone about it for a couple of years because it was the secret of their success. There was Matra in France with 4-valve cylinder heads and wide valve included angles with a great big intrusive piston dome poking up in there like a hand that said, air motion, stop. And in still air, it took 45, 50, 60 degrees of ignition advance to burn it. And all the time that burning gas is trapped between the piston crown and the combustion chamber, heat is roaring out into the metal and being lost. Heat that could have been keeping the gas at high pressure and pushing pistons. So how can a weak little V8 with not enough valve area somehow win the races? Gradually it dawned on them. And then they found out that it was a good solution for emissions because quick burning means efficient burning. You're not wasting as much heat because you're not keeping it contained as long.
You make less knocks too.
Yeah. And now that 4-valve flat combustion chamber has become the standard of the world for cars, light trucks, and motorcycles. We humans try to drive nails with our foreheads, but eventually someone invents a hammer and we're saved. And in this case, the savior was Keith Duckworth, whom I greatly admire, if you didn't know that already. So, because he was an experimentalist, he was not an austere theoretician with his head in the clouds. He was in the dyno room breaking parts, which is how progress is made. Despite the SAE's efforts to interest us in simulating the entire world so that we'll know the time of our own death. The simulation will be so accurate. Have we covered that subject?
I think we did it. Yep.
All right.
Well, we've already gone a little bit through the transmission with our spline shafts and shifting and all that, but we do have dog ring shifting.
Well, the great thing about dog rings is that was how the Indian gearbox in 1911 worked, when with a 2-speed, they won the Isle of Man 1-2-3, confounding the English establishment, Matchless and Company, and leading to a series of great match races, which were long remembered. But the thing about a dog ring is, instead of having to suddenly move a heavy gear lengthwise along a shaft, all you're moving is this little ring that's splined on the inside. It has a groove for the shift fork to engage it, and it has dogs on both faces. And imagine my surprise when confronted with a BMW 1800cc flat twin engine completely disassembled on a clean sheet on the floor. And I went over and I looked at the shift forks and I thought, those look, no, that can't be. So I picked one up. Yes, it was aluminum. So I went over to the engineers and I said, huh? And they said, oh, yes, this is the way we do it now. We found ways to make this entirely practical. Because we, at the dealership, people would come in and say, it don't shift good. You mean sometimes shifting from first to second, it jumps out of gear? Yeah, how did you know? Because the first to second shift has the largest difference in RPM and the greatest amount of force, because the pinion is small. So the gear dogs hit with a terrible force and they bang each other into roundness, so that instead of going together, they bounce off of each other and make your toe buzz as you try to force it into gear. So this will work especially well with automated shifting systems, which are using motor drive to operate the shift drum, to select the gears, and to operate the clutch. And there's software to make this all work. And if you are a purist, you can shift with the shift lever, which is in the normal place. And in that way, your vital fluids will not drain away, leaving you a dry husk of your former self. But if the burden of all that purity should become at any time too heavy, you can let it do it itself. And I particularly like the idea of lightweight shift forks, lightweight dog rings that move quickly into gear rather than ponderously and slowly. we saw a lot of shift forks that were burned blue and black from people tramping on the gear lever to force it to go into second. And if it just goes in, there's no need for that kind of theatrics.
Yeah, we're gonna have to get you on the full Magic gearbox rebuilding tribal knowledge thing. We got to get you to
the tribal knowledge.
we should get that written down so we can make our XS 650 shift properly.
Oh yeah. Well, they're straightforward things. We'll talk about it another time.
Yeah.
But dog ring shifting probably dates back to machine tool gearboxes and to people who were using that kind of thing every day. Well, here's an idea. Let's do it this way. Oh, yeah, that'll be great. We don't have to cut as much metal driving that long multi-tooth broach through each gear to produce the splines. So dog ring shifting was something adopted recently by Kawasaki. I think BMW are using dog rings. Maybe many others have switched over too.
Yeah, I think the short-lived, more modern Kawasaki entry into MotoGP had a dog ring box, which they then adopted for the H2, the supercharged H2.
Yeah.
H2 and H2R, those had dog rings. I wrote the test in 2015 on the street version of that. It was remarkable to ride.
You don't want to miss a shift with a turbo or supercharged engine because there's so much pressure trying to accelerate the crankshaft that if the shift doesn't go through, something may be lost.
Yeah, I called it the world's fastest pressure cooker because there was an intake temperature indicator, and it would get up to, it's compressing the air into the engine, and it would make 250 degrees inside the intake. That's pretty hot, so you could cook a chicken.
This is what charge air coolers are for. People call them intercoolers, but they're not. Unless they're between the stages of supercharging, if there's a multi-stage supercharging system or turbo system. But what they do is they cool the air so that it makes detonation less likely. And in aircraft engines, charge air coolers were common. And if you look at pictures of Miller race cars, you will see sticking out of the right side of the rather long hood on those classic-looking race cars, this folded over, finned aluminum casting. It's just how the air gets from the supercharger to the intake ports, and with some cooling effect on the way so that you don't deliver all that heat into the engine to assist the chemical reactions that lead to knock, 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 knock.
And melt.
Yes, destruction.
All right, next up is, let's see, what are we going to do? We're going to go to, well, I'm a big fan of engine balancers. Let's hit engine balancers.
Okay. One way to balance a single is to have another single pointed the other way and geared together so that the pistons move in opposite directions at all times. And that's what a BMW flat twin is. It's a self-balancing arrangement. Another way to self-balance is to make a 90-degree V-twin that is balanced at 100% of the reciprocating weight. Now, what I do mentally to think about this is I say to myself, okay, the forward cylinder is at top dead center. The other cylinder is in mid-stroke, and the balance weight is directly opposite the piston that's at top center. So they are, in effect, a flat twin. They cancel each other. Then when the second cylinder comes up to top dead center, the counterweight is swung around, so it is opposite that cylinder. So that cylinder is now a kind of flat twin, self-canceling. In a four-cylinder engine with a flat crankshaft, that is 2 up and 2 down, primary shaking is canceled by the fact that two pistons are rising when two pistons are falling. But what do you do about a single? You add weight to the crankshaft at 180 degrees from the crank pin, and it shakes up and down less the more weight you add. But at the same time, now it starts to shake horizontally when it didn't shake horizontally before at all. So what you're doing is you're moving the shaking force out of the vertical and into the horizontal. And because British motorcycle frames were springy this way and
Vertically.
more rigid horizontally, they would balance them not at 50%, or 52%, which is normal for automotive engines, which cuts the peak load on the main bearings in half, but at 65 to 85%, so that essentially you moved the shaking force out of the plane that is unpleasant, makes your feet hot, makes your hands numb, and moved it into the horizontal plane where you don't feel it as much.
And which is why the front wheel on your British motorcycle will shake
Shook
fore and aft.
back and forth in that classic way. And this is one of those things like the boiling point of mercury. When you see it, you think to yourself, God is in his heaven and all's right with the world. So, I mean, you have to rely on something in this information age, something besides information,
Yes.
namely what you can see. So, old man Lanchester, who invented everything, said, why don't we build two eccentric weights that rotate, and we'll gear them together so that they're 180 degrees apart. So now, as they rotate, the lateral components of their rotation will cancel, and all that will be left is a straight line back and forth shaking force. Well, that's what we could use to balance the piston, which is going back and forth in a straight line. We tried adding weights to the whirling crankshaft, and all it did was move the shaking force direction from vertical to horizontal, which can be useful in certain cases. In Britain, the plan was, let's never retool. The Yanks will buy anything, just keep making the pistons bigger. It came to an end in the 1970s, but it worked for a while. So Lanchester's idea was to create a straight line oscillating force that was very similar in character, had a similar waveform to the piston shaking force. And all the world's little four-cylinder banger car engines have Lanchester second-order balancers in them. In my little Korean-made car, they're down in the crankcase and they're driven by a chain. And they don't say anything to me. They don't show up on OBD2 codes. They just do their job. It used to be called four-cylinder buzz, and it doesn't exist anymore because it's been taken out. Now, where does that come from? It comes from the fact that if you attach, okay, we've got the connecting rod with the piston attached to it. If we now move the connecting rod to one side, the piston falls. If we push the connecting rod back so it's straight up and down, the piston rises to its maximum height. If we slide the rod over here, the piston falls again. So that rod angularity is slightly changing the piston height twice per revolution. That is secondary shaking force. And Lanchester reasoned, well, I'll take my rotating eccentric weights and I'll gear them to second order, rotating twice the crankshaft speed. That's what he did. Away went four-cylinder buzz. And
beautifully demonstrated in the Honda Blackbird, the CBR 1100 XX.
Yes, because
that was a
you make them
silky
bigger,
smooth.
make the pistons bigger, and the shaking force gets bigger the engine is the same size as before, so now the engine is shaking more. And you, the rider, are wondering why they put a man on the moon and they can't smooth out this engine? Give me a break. So, Lanchester, 1902, still
Good
with
on him.
us. Yeah.
Well, that Blackbird, man, it was a beautiful bike, silky smooth, lots of power, very peppy, and good juice. It was good, and
like Peppy.
yep.
So that deals with secondary balancers as well, both the cause, which is rod angularity, modifying the piston height, and the cure for it, namely a balancer that produces a straight line force at twice the crankshaft speed, because rod angularity changes twice per revolution. Okay, now we're
gonna combine hydraulic brakes and disc brakes because that's what we all enjoy today.
Yeah, that's true. We do. There have been a lot of attempts to make four-wheel brakes. A lot of ills were blamed on them. Oh, just like when you rode your English bicycle and your friend told you, don't touch them front brakes, you'll go right over the handlebars. Well, then why are they on the bicycle? Well, I don't know. Well, here comes Duesenberg, enters 4 cars for the 1921 French Grand Prix. And there were some ups and downs in getting the entries accepted and so forth, because do we want those colonial boys coming over here to our culture? Anyway, through thick and thin, Jimmy Murphy wins the 1921 French Grand Prix with hydraulic drum brakes on all 4 wheels. In early practice, the brakes worked too strongly on the front wheels, and they thought, are we going to have to disconnect them? Then we'll be just like all these other guys. So somebody said, where's the hacksaw? Yeah, it's in the top of my box there. He saws a chunk off of the brake lining on the shoes, the front brakes, and it worked. Reduced the braking effect. How much should I cut off? About this much. So,
not too much, because you might want to take off more. You can't put it back. Harder to put back.
So they won the race, and hydraulic brakes were validated, and of course, cable or rod operated brakes continued to be manufactured for many years after that, but the technology was validated. It was proven to work. And in the 1950s, when DKW were racing their 350 triple two-stroke, two-strokes don't have any engine braking, so it had these huge drum brakes. Easiest way to operate them and make them powerful enough was with hydraulic operation. So hydraulic brakes on bikes, roughly 1953, DKW. Those German engineers went through an educational system that was fomented by the evil uncle of the Germanic Empire, namely Otto von Bismarck. And even though his backers were pulling their beards at the idea of ordinary people reading books, what if they read the wrong thing? Bismarck said, if you want an industrial revolution like the one they had in England and the power that it gives the state, you're going to have to teach everyone to read. And they did. They created a system of higher technical universities in which everything was related to basic principles, so that it was perfectly clear to those to whom it was perfectly clear. In this country, that didn't include me. I had to get in the shop and see about it. But there were some wonderful theoreticians that came from this educational system, and they continue to come from it. So good going, guys.
No replacement for taking it apart, though, Kevin.
Yeah.
Well, seeing it, you talked about going to see the Honda Grand Prix bike because you got to see it.
Yeah.
Getting in the room with it, or picking up the shift fork.
And better yet, having Nobby Clark tell me all about it.
Yeah, that's solid.
He
Pretty solid.
said when they ran the engines with the valve cutouts in the piston crowns fresh and sharp, they made less power than if you went in there with a grinder and smoothed that all out, which reduced the compression somewhat, but it made those sharp edges slow the gas motion down less, interfered with it less, so the combustion was more rapid and less power was lost to heat flow. So this leaves us with disc brakes. Who do you suppose was an early proponent of disc brakes? Frederick Lanchester. 1902.
Amazing.
I like to think of Chuck Berry, who was invited to Chicago for a gig there, and he took 2 weeks and wrote most of the songs for which he is remembered today. Rousing, good fun music. And it came out of 2 weeks' work. And I think that we see the same thing with John Britton, who said that he liked to work in 5-week stints. There are a lot of people who work in odd ways. They don't just get up in the morning and make coffee and then make a few phone calls to arrange their lunch party. They've got stuff to do. They're thinking of things. They're making it happen. John Britton told me about how he came to make carbon fiber wheels. It just made sense to him to do it the way he did it. And when he took them to the New Zealand vehicular safety outfit and they tried to wreck the wheels in their standard way, they failed to wreck them. The wheels worked because John thought about it. Oh, I can't do it this way because then this bad thing will happen. And he just kept thinking about it. He wasn't thinking about calling up an old girlfriend and seeing if she's still interested. He wasn't thinking about a banana split after lunch. He was thinking about carbon wheels. And carbon wheels are with us today. So there's some value in that thinking. And it isn't that these people like hard work. For them, thinking is play. Play is human activity that has no negative consequence and is undertaken just for the pleasure of it. So much theoretical math comes from this mental play, and so much good engineering. People are willing to think about it, build a test rig, see how it works, refine their ideas, and get somewhere with something that works. So,
Aha feels pretty good.
yeah. Disc brakes. The great thing about disc brakes is they can't get away from the friction material. A drum brake can expand away from it. It can cone away from it. External contracting brakes. The external contracting friction material prevents cooling air from reaching the drum. So, but a disc brake is exposed to the air and it's pinched very firmly by pairs of pieces of friction material with hydraulic force behind them. There have been mechanical calipers built, but not to much effect.
Oh, they were popular on bicycles for a while. They had a lever, the lever on a screw, and you pulled your cable, and it pulled the lever, and it, screwed the pad onto the disc.
Yeah, that could work, particularly if it was a ball screw. A ball screw would be good. So, with that in mind, the idea that the disc can't get away from the force of the friction because it's balanced on either
Yeah,
side
so
of the
post
disc.
pistons are squeezing, or even on a sliding pin, you still have a pretty balanced squeeze.
The F-8F Bearcat piston fighter carrier plane first flew in 1944, and it had disc brakes with triple piston calipers. And originally they were mounted at the bottom of the undercarriage leg. And they found, do you suppose a carrier plane occasionally yaws the moment before the wheels touch down? And then would the wheels receive a lateral impulse? Well, yes. And if the brake calipers are at the bottom, it means that the deflection of the disc is going to knock the pads back. So they move the caliper to 90 degrees to the undercarriage leg. And in motorcycling, we call this radial mounted caliper. Same thinking produced by the same ill effect.
Well, yeah, exiting a corner with a little bar shake. Oh gosh. Honda did with either I think it was the 954, but they coated the front caliper pistons with some low friction coating that was meant to help your brake feel and so forth, give you this really fine feel. But also it made them slippery, and that bike was a little bit more prone when you got some shake to knock the pads back.
Yeah.
And then you go for the lever and like, so it became habit. We balled one up. One of our guys did crash it, but we got in the habit of checking. You just give it a little, you exit and you just like a little breathe. So
I thought that was wonderful that on the F8F, they had to adopt radial mount calipers.
There's a lot wonderful about an F8F.
Well, yes, it's basically an R2800 with as little airplane as possible attached to it.
Yeah, it was sort of 0 to 40,000 or whatever, 0 to 30,000 feet in 5 minutes or less.
4,500 feet per minute initial climb. Yeah, good one.
Oh, God. They had one flying out Palm Springs a few years ago, and whoever the pilot was giving it the beans. He'd come by and it would whistle on a dive, and he was coming by it. It had to be 300 plus miles an hour, and then he would climb, and you say, "Well, that doesn't look right," because he would just disappear so quickly.
Get real small.
Old propeller plane, you know.
So the F-89 Scorpion also was given disc brakes, and that was later. That was 1948. They first flew. And then by 1953, the word had got round, and Dunlop produced disc brakes for Jaguar's C-Type racing sports car. And Duncan Hamilton and one other gentleman whose name escapes me at the moment won the 1953 24 Hours of Le Mans with that car. And the description went like this: the Mercedes, with its enormous and very beautiful finned aluminum drum brakes and a huge aero brake behind the driver that was lifted up by some hydraulic mechanism to produce aero drag, flat plate drag coefficient of 1.0. They're braking, brake. They're approaching the hairpin. Here comes the Jaguar C-Type, still on full throttle. Looks like he's going to crash, but no. The mystery retarders are applied. The car decelerates violently, darts around the corner, and accelerates away. And the Mercedes was unable to do anything about it. So after that, drum brakes were used as bases for floor lamps. Very designerly. I'd like to have one. Those drums with the fins were so beautiful.
Oh, yeah.
And there were all these people trying disc brakes. There was a fellow named Bo Brinker who raced Bull Tacos. He had a weak twin disc system, little tiny discs. The calipers had originally been made as spindle brakes for machine tools. Colin Lister in England made a set for Halewood to test on his 500 Honda RC 181. I just saw this photograph yesterday. And our great late Peter Williams put a disc brake on his G50 matchless 500, along with cast wheels, which he was one of the pioneers, and the resulting motorcycle, which is in Rob Iannucci's shop, is called wagon wheels because, of course, the castings are unusual to look at for someone accustomed to wire wheels. He had a good working system, but about the same time, Honda came out with CB750 with disc brakes. So the concept was validated, and it wasn't long before drum brakes were a kind of special purpose retarder for conditions where you don't want water to get in as quickly or something.
Well, they worked okay, you know. You 1-2 stops, they were not bad. But if you kept putting heat into them, it was I had a '64 Cadillac that had beautiful, gigantic drum brakes, Eldorado, and they were power boosted, and rebuilt them all in new hardware. And God, they were wide and they were giant, and it was elegant braking. But it was also brake fade while you wait, because if you did a really hard stop and you hit them and you were running them, because that's probably a 5,500 pound car. Yeah, and just, 1 or 2, that's all you got. That was the beauty of discs too, is they even with heat, they stay relatively consistent. You can fade a disc brake. You can have the pad friction material change with temperature or something like that, but it's
Ben Spies at Motegi.
so far out there.
Yeah, he turned his brakes into powder in like 3 laps. And in MotoGP, where the brake discs are carbon, that is carbon fiber reinforced amorphous carbon. 1,000 degrees centigrade is the upper limit for reasonable operation, but they've had to increase the size permitted from 320 to 340, now to 355 millimeters diameter. And of course, aircraft couldn't last long with single disc brakes because aircraft move fast and they're pretty heavy in relation to their little tiny landing wheels.
Yeah.
So what did they do? They built brakes that were like clutches, stacks of alternating, rotating, and non-rotating discs with a whole ring of hydraulic cylinders to squeeze the whole stack together. And what happens if the brakes get so hot that the tires burst? Well, there's a fusible plug that's supposed to come out of the rim and prevent that explosion from happening. But carbon brakes for aircraft were developed during the period of like 71 to 76 for commercial stuff. And about 10 years later, they showed up in Grand Prix motorcycle racing, and they're with us to this day. So, more messages from Frederick Lanchester.
Well done, Frederick. Well, thanks for listening, folks. We're going to wrap that one up. We managed to set a near record for length of podcast. It's nearly an hour and 30 minutes, which is just a fraction of 13 hours, but very close. Thanks for listening, and we'll catch you on the next Cycle World podcast.